Okay, good afternoon, everyone. Today we have Punit Singhvi. He is stepping up to present for a last-minute cancellation. Punit graduated from Tapar University in 2010, and then he worked 3 years in the industry before joining our group. He's an expert in asphalt binder characterization and also the characterization of asphalt concrete. So, Punit, the floor is yours.
Thank you, Jaime, for the introduction. Good afternoon, everyone. Today, the topic of my presentation will be around development of a long-term aging protocol for asphalt mixtures, and especially using Illinois Flexibility Index test. Before I start the presentation, just to give you an overview how we'll start and how we'll proceed in the presentation, we'll talk more about how asphalt aging, mixture aging is important, and why do we need this protocol, a long-term aging protocol, and how IFIT fits into this this development protocol for long-term aging of asphalt mixtures. So without further delay, cracking is one of the primary distresses experienced by asphalt pavements, and there are several reasons to it. Material factors can affect cracking significantly. For example, if we use a lot of recycled materials in our mixtures, can make the mixtures prone to cracking. Type of binder used, binder quality, aggregate type, aggregate quality, and overall mix design parameters plays a role in overall cracking, in predicting overall cracking of the mixtures. These factors can still be controlled at engineering level, whereas there are certain factors like environmental factors, like change in thermal gradients. In Illinois, we experience extreme heat, extreme temperatures, both extreme of temperatures. Whereas aging sounds to be a small word like aging, but it is a highly complex phenomena, and we'll dwell into what basically aging is. So these factors, like environmental factors, also play a role in asphalt cracking. So with a background, in 2015, we developed here at ICT a test called Illinois Flexibility Index test using a semicircular bending specimen geometry. And the test was kind of a good indicator for cracking performance. The test was conducted at 50 millimeter per minute of monotonic loading, and it resulted in parameters which is useful for predicting cracking. This is a short video of showing how the test is. It's a very simple test which was developed, and as you see, there's a seating load applied onto the specimen, semicircular specimen, 15 millimeter of thickness with a notch depth of 15 millimeters. Apply a seating load, and then you apply the load at a rate of 15 millimeters per minute. What you get is a load displacement curve, and this load displacement curve can tell you a lot more information about the cracking potential of a mixture, asphalt mixture. So two main ingredients of this plot is, one, the work of fracture, which gives fracture energy, and the post-peak behavior of this load displacement curve, which is basically the slope of inflection, will tell you about how flexible the mix is. And this flexibility, higher the flexibility, better cracking susceptibility. This test, when developed, was used to characterize mixtures with high recycled materials, and it was observed that it was shown that this index works well in discriminating mixes. It was validated with field correlations, and it was even evident when the samples from field cores across Illinois were collected and tested for IFIT. So the field core correlation showed that with increased aging, as the asphalt ages, the flexibility index drops, and which kind of correlates to the idea that yes, it can work as a cracking test. So when we lay a new asphalt pavement, it is exposed to, apart from material properties, material changes, it is exposed to some constant phenomena like weather, UV exposure, moisture, which in due course changes our asphalt pavement. to much light colored cracked section. Now this change is variable depending on how these parameters are affecting, and this can be delayed, this can happen quickly as well. So what is the underlying problem? The most important ingredient which has experienced this change due to aging is the asphalt binder. Now asphalt binder is a very complex material. It is a hydrocarbon, a mixture of hydrocarbon which is composed of basically 4 fractions. That's how we divide asphalt binder, which is resin, saturates, aromatics, and asphaltenes. Now there's no unique chemical structure for asphalt binder, and that's what gives the complexity, that these chemicals, when acted upon by the natural phenomena like weather, change in temperatures, moisture, and then UV exposure, that is the ultraviolet exposure, and I will come later in the presentation how that affects this change in chemistry. So this basically structure changes over time, and that can cause your mixture in effect to perform better or poor, depending on how these properties are changing, how these chemistries changing. Another part is binder modification. We are experiencing this quite often, that the binders used in the construction are modified either with polymers, with softeners, based on the target goal, even WMA additives. And so these modification again causes change in chemistry, and this chemistry, due to the action of those natural environmental factors, can result in differential in aging, which can differ from binder to binder and mix to mix. Even the crude source plays an important role. Now, asphalt aging, as I said, is a very complex phenomenon. Now, what can happen in asphalt aging? Thermal degradation is one of the reasons where your asphalt binder can degrade. And what thermal degradation is, as name suggests, higher temperature will lead to breaking of these molecules, these large hydrocarbon chains, based on how high you are at temperature, and that can cause binder to behave in a certain way. The most important part is chemical degradation, which the binder is experiencing most part of its lifetime. Now, one part is photooxidation, and that's where I was talking about UV. So UV rays basically provides energy, and this energy is capable of creating or causing an oxidation reaction, and that's why it is called photooxidation. Now, visible light spectrum doesn't have that energy which can initiate that oxidation, and that's where UV is an important parameter for chemical degradation. Another reason for oxidation can be thermal oxidation. Oxidation needs energy, and it can be provided by thermal energy as well. So in summers, if you'll experience in Illinois, we've experienced temperatures, pavement temperatures up to 120 degree Fahrenheit, if I'm not wrong, right, Mike? Higher, 140 Fahrenheit. And that temperature is typically enough for the oxidation reaction to happen. And that's why it is a very variable phenomena depending on place to place and region to region. Hydrolytic degradation refers to moisture damage. Now, presence of water, again, in the presence of heat or energy source, can cause the binder to react with water and then further degrade the binder. So all these phenomena are happening at the same time and can result in asphalt aging in general. So it's, as said, highly complex phenomena. So with this idea in mind, that the way asphalt ages and how the chemistry affects, this will have definitely an impact on the performance of overall mixtures, apart from what material or mix design parameters will introduce. So there was a need to develop a long-term aging protocol for asphalt mixtures and determine the flexibility index thresholds, because we saw that flexibility index or IFIT test is capable of distinguishing mixtures with different cracking potential, and with aging we see a lot of cracking happening. So combining these two, today I will talk more about how the aging protocol will work, not about the thresholds, because we are still working on that. So we need something like an IFIT test in a laboratory environment to expose the natural happening conditions like changes in weather, UV rays, and we need to monitor, we need to mimic these conditions inside the lab so that we can come up with a protocol, and over time it will result in an aged sample or aged mixture. Now there are several challenges. As I said, photo-oxidation is one of the processes or one of the methods where you see differential aging happening across different regions in the United States. So this is a UV index shown for February, and if you see that this UV index, first of all, is different in different parts, and also it changes with different times. Like if you compare it with August to summer to winters to fall, this index will change, and this causes, again, a variation in aging. Apart from that, within the asphalt structure, you have differential aging, which needs to be addressed. And that's where, when the surface is exposed to all those natural phenomena more than the lower surfaces, and that's where this aging gradient comes into picture. So that's where we look for a protocol which can kind of answer all those problems and yet be easy to implement, reliable, and give reproducible results. Should be cost effective so that it can be adopted easily, and should be practical enough, and at the last but not the least, should correlate to the field and all those variable phenomena. So for this project, we started with several mixtures. So in the current scope of study includes several plant mixtures and field cores where these plant mixtures were placed. And we also designed several mixes inside the lab to answer some of the questions like effect of binder source. In order to develop the aging method, we need an aging device. So there are certain devices which are already available which ages asphalt binder, but not for the mixture. For example, PAV is used for binder aging, whereas vacuum oven is prominently used for sealant aging. Forced draft oven was one of the options for mixture aging. It was considered as because of its practical reasons. And then another device, which is the UV device TH, which was recently developed by one of our peers from Portugal, visiting scholar, and he developed this device of UV aging, which is capable of providing UV exposure at different rates and also can accommodate effect of moisture. So this is something which is under research, and this was provided by one of our students here. So these all methods were taken together, looked into, and there were some outcomes from this this investigation, preliminary investigation, that PAV wouldn't work for mixtures because of its capacity, and also if you use a sample which is a finished sample and put it in the PAV, you will see that there's problem with specimen integrity. Vacuum oven was considered, but because again, due to the limitation of capacity of material it can age, was eliminated. UV device is still under investigation, and we are looking into it because it's somehow can predict how UV or the real-time aging can change the mixture properties. So we were left with so the most viable option we had was forced draft oven. Now with forced draft oven, asphalt mixtures, to age the sample, we need high temperature because that will provide energy, and then forced draft oven has air flowing into it, which is the source of oxidation, so which can somehow mimic the real-time aging. We had option either to use a mixture which is loose or compacted. So this is a compacted specimen used directly to age the sample in the oven, or first age it in a loose condition and then compact to get the sample. With a thorough study, again, the loose mixes were eliminated for the sake of the study due to the following reasons. First, the high operation variability. It has benefits, but it has its cons. That is the variability, which was our concern. The pros are, yes, definitely there's no aging gradient because you put it loose into the oven. You make sure that you stir it in a regular interval so that the material is not having any aging gradient across the depth. Second, the specimen integrity was maintained because you age the sample and then you compact it. And loose mixture aging is more kind of an accelerated aging, which can help you age the sample faster, which is good, but again, high operation variability. Whereas on the other hand, compacted specimen has its pros and cons. The pros were limited operation variability. Once you prepare the sample, IFIT sample, and then just place it inside the oven, and that's it. It ages. So there's no operator variability is involved while the aging is happening. Whereas in loose mix, you have to stir it every hour or every day based on how your protocol will be, and which can be variable from operator to operator. There are cons like specimen integrity and differential aging. So the sample will be aged differentially across the specimen, specimen thickness, but this is irrespective. This is consistent with all the mixtures you're testing because there's no operator variabilities involved. Specimen integrity can be taken care of, and I will talk about this in the following slides. So two things which will help a protocol to come up for post-draft oven is temperature and duration, because temperature will give the required energy, and duration will decide the exposure of that oxidation happening at that temperature. And as you increase the temperature, the rate of aging, the energy you're providing for oxidation is more, and that creates more oxidation, and we want something to be more practical that can age the sample faster. So we always shoot for higher temperatures, but there are limitations. You cannot go too high, and we'll talk about that. Again, the duration, higher duration, you age the sample more, but you cannot go 7 days or more because it will practically will not be viable. So with that idea, we decided to go with compacted specimen, and we observed that anything beyond 110 degrees Celsius can hurt the specimen integrity. So that's why temperatures higher than 110 degrees Celsius were eliminated. There's another study which was conducted by NCHRP, and which said that when mixtures are exposed to temperatures higher than 100 degrees Celsius can lead to change in chemistry of the binder in the mix, which is not correlated to the field, and that's where they prefer to keep the temperature below 100, and that's why we came up with the idea, okay, let's keep 95 degrees Celsius as an optimum temperature to look into, so that higher the temperature but doesn't change chemistry and maintains the specimen integrity. As far as duration was concerned, the current Astra procedure for long-term aging states 5-day aging at 85 degrees Celsius. Now 5 days is too long of a time, so we need to reduce that time. So that's why reduced times like 1 day, 3 days were considered in this particular study, along with the current Astra procedure. Now, the important question here to ask is whether these selected duration and time will actually relate it to the field aging or not, which is a big question still need to be answered. So for that, there was a pilot study which was run that in the draft oven, is there some sort of oxidation really happening or not? And to do that, we used several gases, argon being an inert gas, nitrogen, air, and we tried to age the sample with the temperature selected and the duration. And it was observed that when in the presence of inert gas, even at temperatures like 95 degrees Celsius, higher temperature enough, the Fi values doesn't change, or flexibility index value doesn't change for different durations, which means that temperature is not there's no major thermal degradation happening, and it's basically oxidation which is happening in the mixtures, and that's what a good sign that post-draft oven can be used as an oxidation device or as an aging device. Now I'll dwell into the results that will tell us how this flexibility index can help in distinguishing mixes with different aging potential. So to start with lab mixes, 7 lab mixes were designed with different recycled contents, and in order to observe the effect of source variability, which causes changes in chemistry, binders with the same grade but different sources were also selected. It was made sure that the volumetric properties of all these mixtures are same, and the aggregate source corresponding for all these mixes are same, so there's no variability coming from the mix design parameters or the aggregate source. So typically what we found that with temperature increase we saw a reduced Fi, and with duration increase we saw a reduced Fi, which is kind of intuitive, based on how the material will age and how the Fi will decay with time. So out of those temperatures, few temperatures were selected for the continuation of the study, and I'm just showing few of the durations and temperature combinations which were studied in this project. So the lab mix results, if you look here, out of these 7 mixes, the decay of Fi was evident in all of the aging conditions. So as you increase the severity of aging, there is a decline in Fi, which makes sense. Also, the effect of binder source was clear. If you compare mix 1 and mix 2, if you see, these mixes are same. The only difference what it has is the binder source. And M value is somehow telling you that this binder source is kind of different from the other. And better the M value, better the relaxation properties, better we expect the cracking susceptibility. So better for cracking if you have a higher M value, and which is evident if you compare 1 and 2. But when you compare 3, 4, and 5, again, these are same binder grades but different source. And if you see, this M value follows some sort of trend and clearly follows the trend with the Fi. So interesting result that binder source does have an effect on Fi and unaged Fi as well as with aging, and also with the effect of ABR was also observed here. If you compare mix 6 and mix 3, they are the same mixes except the ABR content. Even the binders are same. So you see that effect is pretty clear. So for the lab mixes, when these aging conditions were compared, it was observed that the current protocol for ASH2 R30, that is 5-day 85C for long-term aging, correlates well with 3-day 95C, which was looked into this study, and 1-day 95C, which are much more shorter duration, more practical than the existing 5-day 85C, and they correlated well with each other. One of the important parameters which was studied and observed in this study was aging rate. So the amount of duration you age and the temperature you age the sample, the rate of aging is highly affected based on the duration and temperature. And aging rate is pretty much defined as the unaged Fi to percent change of unaged Fi compared to the aged Fi. And if you see here, 1-day aging has a higher discriminating potential in distinguishing mixes compared to either 3-day or 5-day, which basically tries to be consistent for almost all the mixes. So in order to differentiate these mixes, which are different within itself, 1-day 95C was somehow performing better in terms of determining which one is good, which one is bad, whereas the other conditions were somehow not able to tell that able to differentiate that. So some observations from the lab mix study gave us the idea that the rate of change is pretty high for 1 day, that the 1-day 95C condition, and has more aging potential, more discrimination potential for cracking, whereas all of these 3 conditions which were looked into somehow correlated well within itself, and 3-day 95C and 5-day 85C appeared to be equivalent. And aging rate plays an important role apart from just the final value of flexibility index. So this needs to be taken care of in the protocol which will be designed. Other observations were ABR effect was observed, and then impact of Fi on due to binder source using M value as a parameter was evident in this study. Then the plant mixtures from various end designs and different type of mixes, being SMA and coarse graded, with different binder types, was considered in the studies to see whether this protocol works, the suggested. So the plant mix results also shows that for all these 3 aging conditions which have been shown here, 1-day 95, 3-day 95, and 5-day 85, the Fi decay was evident in almost all of the mixes. But this rate of change of Fi was different for different mixes. And Again, the correlation to different aging scenarios were in alignment with each other. If you look into the aging rate for plant mixes, you will see much more discrimination potential, much more variations for 1-day 95C, because these mixes are different. SMA mixes, coarse graded mixes, binder from polymer modified to unmodified binder, and again 3-day 95C and 5-day 85C somehow for most of the mixes somehow landed up resulting in the similar reduction rate or aging rate. So 1-day 95C has a good potential of discriminating mixes. Even the mix design factors were easily identified from the statistical analysis, that VMA has an effect, mix type has an effect, effective binder absorbed has an effect on the aging rate, which makes sense that here more the absorbed asphalt, lower the aging rate, because you have a more binder film thickness on top of the aggregates, which will lead to decrease in aging rate, which is good. So in the end, based on this study, what we found out that forced draft oven can work as a viable option for mixture aging, whereas PAV and vacuum oven had some practical disadvantages. UV device, which is still under consideration, is under research and will be looked into. Out of the type of material you use, either in a loose state or a compacted state, compacted specimens were preferred due to its advantages and less variability. And important parameter here, the temperature should not go more than 100 C in order to maintain that specimen integrity, and at the same time the change in chemistry happening because of the higher temperatures, so that you can relate it to the field. There are several factors which were seen affecting aging, like temperature duration and what temperature. And as it was seen that if you increase the temperature, aging will increase the duration, aging will increase. Binder source had an effect on FI, which was seen from the lab mixes and were clearly evident. And the rate of aging, that is the aging rate, and the FI decay were statistically significant for properties like VMA, mix design parameters like VMA, absorbed asphalt, whether the mixture is coarse graded or SMA mix, or even the low temperature grade and aggregate absorption. So in order to develop the protocol, based on the study we conducted, there's a few takeaways that 3-day 95C and 5-day 85C were kind of giving more stable values, but stable FIs, but 3-day 95C being more practical. And each of these aging conditions correlate well with each other, was preferred for a long-term aging protocol. Is considered for long-term aging protocol. And however, this 1-day 95C aging criteria can work as a good indicator to discriminate mixes, and that needs to be considered along with the aging rate at that particular aging condition, because that can help in distinguishing mixes from good to bad. But it is not enough of aging provided for the long-term aging. So that's why 1-day 95C can be a good indicator in discriminating mixes, but not work as just a long-term protocol. For the future works, we're still working on selection of the aging protocol, and then FI thresholds needs to be determined for the selected protocol. Field validation is underway, and we're testing cores from the field, but still we need more cores in order to validate that long-term aging. We are in the process of applying the TH device, which is a UV device to simulate real-time aging at the same time. And later works will also include the binder characterization of those mixtures, because chemistry, as we said, plays a very important role in determining the aging potential of the mixtures, and that's where this binder characterization needs to be done as part of the future study. And would like, in the end, I would like to acknowledge the IDOT for sponsoring the project, and then our research engineers, faculty, and staff at ICT, where you see, and there are several students involved in this project, and thanks to them for making this project successful so far. Thanks to Singhvi, Muhammad, Arturo, Uthman, Isaac, Panda, Fazal, Jose, and the name goes on. There are several other names if in case I missed it. Sorry about that. But yeah, I'm open for questions.
Does anyone have any questions for Punit?
Okay, Mike. Yeah.
There was a slide, and you were, I think, comparing lab mixes. It, indicated that the aggregate structure was the same, but changing the percent of ABR. I guess with that ABR, you're also introducing that aggregate portion from RAP. Is there any chance that there's a significant enough difference in the aggregates coming from RAP that it could influence your performance?
Yes, that's possible, and that's where the ABR content was kept low up to 20%. So around 25% of RAP was added. Definitely it can introduce that aggregate variability, but gradation point of view and volumetrics point of view, those were kept same. So if we need to compare, so that's why we had that subhead where, let me go back to the slide, where we had that subhead, we were comparing 2 mixes at a time or 3 mixes at a time, so that it's, so if you look here, so these mixes have the same RAP. So we can easily compare this, but I cannot compare this to this directly because of that reason of the recycled content, and then binder is changing, grade is changing. But yes, that's a valid point that if you have higher ABR, then you will see much more differences coming, just not from the binder source, but also from the RAP. That's true. Yeah. Thank you.
I have a general question. So here in the work that you presented, you talked about 2 important things. You talked about the chemistry after aging, and you talked about the performance after aging. And this work, I think, is mostly the performance and not the chemistry.
Yes.
How do you think that these 2 factors play together? Like, for example, because I'm not very familiar, like if the chemistry is the same, does the performance will be the same?
So this is something which we need to answer, and that's where, like, so for example, if chemistry is same, exactly the same, it is expected that it should perform same, keeping all other factors are same, like mix design factors and all those things. But that's what doesn't happen in reality. The chemistry of asphalt binder doesn't remain the same. And that, yeah.
But what's more important then? Is it the chemistry or the performance at the end of the day?
Of course, the performance is important, but chemistry is somehow associated with it. So if you have a mixture, for example, if you have a binder modification with something which is like a cooked oil, because oil is kind of an hydrocarbon, you can add that. So in long term, the change in that chemistry for different binders can change, because chemically they're different. There's no one unique structure for asphalt binder, chemical structure. So that variability will eventually affect your rheological performances of the binder, and that affects the performance. So here with IFID, we're trying to measure the performance, but at the same time we need to validate that yes, does this chemistry plays that role, and how we can incorporate. If we understand the chemistry, can we improve the performance? Something. So it's like kind of supporting your performance. The test, the protocol will tell you whether it perform or not, but at the same time we need to understand what is the fundamental behind these changes, and can we somehow engineer that.
Thank you.
Next presentation. I have a question about the UV effects.
Yes.
So what's the mechanics of the UV effect on the aging? Is it because of the heating that the UV is producing, or it has some kind of special mechanics?
I would use the analogy like, for example, how you take an X-ray image, you bombard with the X-ray beam, which is having a specific energy, and that removes the electron out of it from the material, and then it somehow makes the image, right? X-ray. Similarly here, UV is an energy source. It has a wavelength from 300 to 400 nanometers. Now that energy, when hits the asphalt binder material, asphalt binder, it causes that reaction, oxidation reaction to happen. And this is from one of the literature, I can share the literature. And it said that in order to have that photo-oxidation to take place, you need energy from somewhere from, I think, 400 nanometers to some nanometers, that energy. And UV falls under that range. And that's why UV causes that photo-oxidation.
So it's not the heating that causes.
So I mean now, like heating also causes oxidation.
Yeah, I mean by UV.
But UV, whether it's just heating or it's causing that reaction, I mean still, I don't have an answer to that, whether that UV is causing the heating, but most likely that UV is an energy source, which hits the asphalt material and which makes the process. So, and as far as I see that based on the literature, they define photo-oxidation especially happening because of the because of the wavelength of the light which is hitting the material, and that's where it is making this reaction possible. And thermal oxidation is something else, which is just because of the heat you have some energy, and then the oxidation is taking place. Yeah.
Another question.
Yes.
So usually now when we talk about aging, everyone talks about like UV. We talk also about like the PAV, RTF4,
Yeah.
and all of these methods. And then we are trying now with the new machine that you were showing
Yes.
to add like the moisture and the UV together to
Can be-
simulate what's happening in
Yeah.
the field. But my question is, how is it important? Like at the end, if any technique, even if it's very simple, at the end, if it's giving me the same chemistry as the aging, like the binder, H binder, why does it matter to put all of these conditions?
Okay, valid question. So thank you for the question. Very nice question. So the thing is, we need to develop the fundamental science behind this mechanism. I mean, we can do another test, we can correlate, and we can check the performance. But there is an underlying performance, underlying like fundamental mechanics behind this aging, and that's where we are trying to validate. Because right now, whether 5-day aging, 85C is real field aging or not, and actual pavement performance is not just the surface mixture; it is the performance of the entire structure, right? So, I mean, right now with these tests, we can talk more about just the mixture which you're placing on the field, not about the entire structure. So that's why it is important to support it with more fundamental mechanism, and eventually use a simple technique which can somehow be, simulates that field effect. Because right now we don't have a benchmark that whether this aging is real aging or not. Just based on performance, you cannot say that. You need to relate it to the mechanism. It should answer through mechanism as well. That's what I think. Yeah. Jose, you have a question?
Where do you see that this aging protocol is going to be implemented? You guys are doing this to do it for plant sampling, or is control the mix to the process? Like what at the long term, where do you guys see this protocol going to be implemented?
Thank you for the question. The question I'll just repeat. So, what's the use of this protocol? Where it will be implemented, right? So, the possible implementation is for the plant production, where they produce the mixes on a regular basis, huge mixes, and they want to make sure that their quality is maintained before they place the mix outside. So you need a more reliable and practical at the same time. You cannot have a protocol which can tell you in a month's time that, okay, this is your result, but the payment is already late. So you need something quick. And at the same time, you need the protocol for lab purposes, because that's where you are designing your mixes before it goes for the production. So these protocols will help to take required measures that whether this mixture will perform over time or not, and that's where it is implemented, like mostly at production level and like design level. Any other questions? Right.
So if no one has more questions, thank you, Punit.
Thank you.